So hello to both of you. I'm Rémi, nice to meet you. And can you introduce yourself, please?
Sure. Bonjour Rémi, je m'appelle Glen Campbell et je suis chef d'équipe d'architecture de solutions et c'est une partie de notre groupe, c'est l'architecture et stratégie à AMD. Et nous avons avec nous aussi mon confrère, c'est Michel Bennett, and Mike can introduce himself.
Hey, I'm Mike Bennett. I'm a solution architect here at AMD. I focus on cloud-native technologies.
OVHcloud right now deploys a lot of bare metal servers using AMD CPUs. How do you project into the fact that it's used for containerized workloads? How does it help the end customers?
There's a couple of really good pieces we try to have folks understand first. Number one, in terms of why they consider AMD. Number one, I expect we all understand, containerized are just processes. So when we look at why people consider us, we take the standard things that makes sort of AMD some success in the market around whether that's performance per watt, performance per euro, per pound, per dollar. Those measurements we've been sort of industry leading for 2 or 3 generations. So sort of first generically, they look at it because if you've got a workload, we're the leading platform for people to run it on. That's the generic. Specifically, a number of generations ago, we started looking to understand there's an interesting piece with cloud-native workloads where the data that gets processed comes over the wire, is remote. And when I'm done, I send it over the wire. That's remote. Some of that actually really drove our 128 core, our now 192 core boxes with much more tailored layer 3. So we began to look at the applications common in cloud native and what the right CPU architecture to match that up would look like.
And now the way that we develop applications using mostly containerized workloads, does it change the way that you are doing R&D and the way you think to shape the future of the architectures?
Without question. One of the things, again, that we like about the Kubernetes world, we all understand Kubernetes effectively does one thing. It's a desired state engine. You tell all the myriad pieces. An operator tells it what it wants, a user tells it what it wants, the application tells it what it wants. So AMD looks at the world as fundamentally, this is a platform, and we try to understand what are ways that we can help that platform be optimized. One example is a power manager. This is Kubernetes controller, it's an operator pieces. What this fundamentally is doing is saying, let's try and protect some of the power headroom that we know full well AI workloads are going to be happy to consume. So we look at things where there is energy affinity to where I place the workload. I have the ability to spread my workloads so I get my target idle powers. So we're looking at the world not just in the CPU, but where is it used, what is the wider landscape. So we've got a core project that helps look at it this way too.
So looking at your roadmap and the way you are going to implement new things for cloud-native world and containerized workloads, how is it working and what's your next plans?
Yeah, so one feature that I'm working on is our platform quality of service, or PQoS feature. This allows for resource control of memory bandwidth and cache allocation, which is traditionally not something that the Linux kernel handles itself. As organizations look to optimize the density of application deployment on their systems, using PQoS can help them get more density by co-locating compute-bound and memory-bound workloads together and providing quality of service guarantees to make sure that the tier 1 workloads get all the memory bandwidth they need and that the noisy neighbor impact is minimized. Some other features that we're working on are around enhancing AI deployments on CPUs for inference so that customers can use their general purpose Kubernetes environments to power AI agents and deploy them in their application workflows.
That's cool. And how do you think the way you develop and implement your CPUs can debunk or unveil some myth?
One of the ones that crosses our minds is that we do hear with 128 core, 192 core, pending 256 core models, the question comes up, what about what's known as the blast radius? What happens if a node drops out of the cluster? And our general look at that is Kubernetes from its very beginning has always understood about node management. Whether you're dealing with a stateless or stateful application, there is long-standing maturity there to account for what happens if I need to take a node out of operation. with that as a sort of well understood operational model, the concern for how do I handle when one node, whether it's 128 cores or 2 cores, the concern for that is well understood. So while people, when they begin to look at the density, which is actually a positive thing, you can actually have better performance per watt. Some of the things that people are paying for, it is optimized for that. And we just try and highlight that Kubernetes as a platform is extremely well positioned to account for any of the availability pieces that we all know we deal with anyway.
And what would be your inputs on things that were improved or to have better understanding for the people using your products?
Yeah, I think there's been some misconceptions about x86's ability to deliver the power efficiency and density required by cloud native workloads. But as we've seen with our latest 192 core, 384 thread parts, x86 can definitely be adapted to meet the needs of cloud native workloads.
That's pretty cool. And thank you, both of you, to join us and give us some time for this interview.
Thank you so much, Remy. This was fun.
Thank you very much. Merci. Thank you.
Merci, monsieur.